Hello student, myself Anirudh Dobriyal, PGT Mathematics. Student, today we will do chapter number 1. It is real number. It is a very good and interesting chapter. So first of all, I want to discuss its introductory part. Study it in previous classes, but I am revising some of the topics which is important to this chapter. First of all, you should know what are the types of numbers. So first number is a type which is whole numbers. So student, whole number started from 0 to infinity, 0 1 2 3 4 5 6 up to infinite, you can say, and it is generally denoted by W. So set of whole number will be denoted by W, and it is 0 1 2 3 up to infinity. Then another number we have natural numbers. It is denoted by n, and numbers are 1 2 3 4 5 up to infinity. It is start from 1 and whole number start from 0. Now another numbers we have even numbers. Though number which is completely divisible by 2, remainder should be 0. In that case it should be divisible completely, then it is called a even number. Examples we have given: 2 4 6 8 etc. are the its example. Odd numbers, number which is not even or not divisible by 2 is called odd number. A number which is not even, that is odd. Example 1 3 5 7. Whichever number is not divisible by 2, that are odd numbers. Now another type we have integers. Integer is generally denoted by I or Z. So it is equal to start from minus infinity, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4 up to plus infinity. It means minus infinity to plus infinite numbers will be integers. Not. Now you have to keep one point in your mind, that one is neither a prime number nor a composite number. Now what is a prime number? We have a number which is divisible by itself only, that is prime number. Like example of prime numbers are prime number. First prime number is 2, and 2 3 5 7, then 9 is divisible by 3, 10 is 11 13. These are prime number. And what are composite number? The number which is not prime, which is divisible by 2 or 2 number, then it is a composite. Now student, we have another number, rational number. A number of the form p upon q, where p and q are integers and q not equal to 0, is called a rational number. What are the examples of rational number? 3 upon 5, 11 upon 7, minus 4 upon minus 7, 8 upon 9, etc. This type of number, it means fraction type of number, is rational number. Or we have written here, q should not equal to 0. If q is 0, then its value will be infinite. So that's why q should not equal to 0. Now what are irrational number? A number which is not rational, that is a irrational number. So examples are root 2, root 3, root 5, root 7, root 8, root 11, root 17, whose root cannot be find completely. That is a irrational number. Now the chapter name is real number, but we not discussed about real number. You are thinking, student, whatever numbers we have discussed till now, all are real number. Number discussed about all are real number. So it is not any different number. These all numbers are real number. One point you have to keep in your mind, there is another type of number, that is called complex number. We will discuss about this complex number in class 11th. Now student, in this chapter we have a theorem, Euclid division lemma. What is the theorem? It states that any rational number a can be divided by another natural number b, leaving a quotient q and a remainder r, which should be less than b. So we can write like this: a is equal to bq plus r. A is equal to bq plus r, we can write. And student, this is not anything new. You are doing in your previous classes. It is like if you have to divide 13 by 4. So 4 3s are 12, 1 is remainder. So you can write 13 as 4 into 3 plus 1. One more example we can take. If we are dividing 15 by 3, so it will be 3 5s are 15 and remainder 0. So we can write 15 is equal to 3 into 5 plus 0. So remainder will always less than equal to the divisor from which number we are dividing. So we can say that dividend is equal to divisor plus quotient plus remainder. By this example we can clearly observe. Now you can dividend is equal to divisor into quotient plus remainder. Now I have written here one more example. When we are dividing 43 by 7, so it is dividing 6 times and 1 is remainder. So we can write 43 is equal to 7 into 6 plus 1. So 42 plus 1 is equal to 43. Now one more example we have here. 32 when divided by 8, so it is completely divided by 4 times and 0 is remainder. So we can write like this. 32 is equal to 8 into 4 plus 0. So this is coming 32. So left hand side is equal to right hand side. So you have to remember that remainder will always less than that number from which we are dividing any number. One more theorems we have given in this Euclid algorithms. So what is this Euclid algorithm? Euclid division lemma provide a stepwise procedure is known as Euclid algorithm. Student, Euclid follows a different method for finding SCF, that is Euclid algorithms. So in which we have given two numbers and we have to check which one is less, like 135 is less than 225. So we will divide by lesser number that greater number. So we will do like this. 135 into 1, 135, 90 is remainder. Then we again divided by 90, 135. So it is coming 45 is remainder. Then we again divided 90 by 45. So it is completely divisible here. Divide here. So we can write like this. 225, 135 plus into 1 plus 90. 135, 90 plus 1 plus 45. 90 is equal to 45 into 2 plus 0. So 0 is coming here. So this one is SCF. In which step 0 is remainder, that will be the SCF of those number. Now one more theorem we have, the fundamental theorem of arithmetic. It is related with the factorization of natural number. It states that every composite number can be factorized as a product of prime uniquely. Like you have 24, so you can factorize this like this. 2 into 2 into 2 into 3. Like 50 is equal to 2 into 5 into 5. So this is the fundamental theorem of arithmetic. We are doing chapter number 1. So its question number 1 is use Euclid division algorithm, find the SCF of 135 and 225. So first of all you have to see which number is greater. So 135 is less than 225. Then you have to divide greater number with lesser. So we are dividing 225 by 135. So it is dividing like this. 90 is coming. Again you have to divide 135 by that remainder which is coming. Now one time it is dividing, so 45 is coming. Now you have to divide 90. Previous number from which we divide, we have to divide after and after. So it is completely dividing by 2. So 0 is coming remainder. So you have to divide till 0 is coming. So we can write this like 225 is equal to 135 into 1 plus 90. Dividend is equal to divisor into quotient plus remainder. Then 135 is equal to 90 into 1 plus 45. Then 90 is equal to 45 into 2 plus 0. So 0 is coming, remainder is 0. Hence SCF of 135 and 225 is 45. So this is our required answer. Now we are taking its third part. What is the third part? Find SCF of 867 and 225. So you clearly observe that 225 is less than 867. Now we are dividing 867 by 225. So it is going 3 times. 102 is coming. Again we will divide 225 by 102. So it is 51 is coming remainder. So again 102 by 51. So it is going dividing 2 times completely. 0 is coming remainder. So we can write like 867 is equal to 225 into 3 plus 102. 225 is equal to 102 into 2 plus 51. 102 is equal to 51 into 2 plus 0. So SCF is 51. So this is the answer of this question. Now student, we have question number 2. So that any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5, where q is some integer. Now it is a very good question. Let a be any positive odd integer which is divisible by 6. After observing its type, we can clearly observe that it is divided by 6, because if b divide a, then it will come a is equal to b cube plus r. So according to this, b is equal to 6 is here. Now then what is the type? It will be a is equal to b cube plus r. This is the type when we are dividing it by 6. Student, you always have to remember that whenever any number is dividing by any other number, then remainder will be always less than divisor. So it is dividing by 6, so remainder will be 0, 1, 2, 3, 4, 5. Remainder never come greater than that number from which we are dividing. So till 5 remainder is coming. So according to this, a is equal to 6 cube plus r. What is coming when r is equal to 0? A is equal to 6 cube is coming, because r is 0 here. R is equal to 1. A is equal to 6 cube plus 1 is coming. R is equal to 2. A is equal to 6 cube plus 2 is coming. When r is equal to 3, a is equal to 6 cube plus 3 is coming. When r is equal to 4, a is equal to 6 cube plus 4 is coming. When r is equal to 5, a is equal to 6 cube plus 5 is coming. Where q is any quotient. It may be any number, but we can observe here that a is equal to 6 cube, we can take common 2 in this. So in any number which is 2 is coming common, then that will be an even number. So it is a even number, because it will be cancelled out by 2 easily. 6 cube plus 2 is also a even number, because 2 is coming common. 6 cube plus 4 is also a even number, because 2 is coming common. Hence these cases are rejected. A is odd integer, because we have to prove that it is an odd integer, but these are even, so that's why they are rejected. So therefore any positive integer of the form is 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5, we can say, because these are rejected. So remaining cases will be the required cases. So these are the cases, hence this question is proved. Now student, we have question number 3. What is the question? An army contingent of 616 member is to march behind an army band of 32 member in parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So in this condition, we have to find its SCF. Let's see. In order to arrange the two groups in maximum number of columns as required, we should find the largest number that divide both 616 and 32, and that is their SCF. So SCF of 616 and 32, you clearly observe that 616 is greater than 32, then we will divide 616 by 32. So 8 is coming. Again 32 divided by 8, so 4 is coming, 0 is remainder. So 616 can be written as 32 into 19 plus 8, and 32 is written as 8 into 4 plus 0. Therefore the SCF of 616 and 32 is 8. Hence the maximum number of columns is 8. This is a very good question and very important also. Now question number 4, we have use Euclid division lemma to show that the square of any positive integer is of the form 3m or 3m plus 1 for some integer m. So student, let a be the any positive integer. We apply the division lemma with a and b is equal to 3, because after observing itself we can clearly say that it is divided by 3. Now when we are dividing a by 3, then remainder will be 0, 1, 2, because it should be less than, are always less than divisor, so it should be 0, 1, 2. So a is equal to 3 cube plus 0. On putting a is equal to 3 cube plus like a is equal to 3 cube plus r it should be. So when we are putting remainder here, so a is equal to 3q, a is equal to 3q plus 1, and a is equal to 3q plus 2 is coming. Now we have to square these numbers. So case 1, when a is equal to 3q, squaring both sides, a square is equal to 3q whole square, so it will be 9q square. We can take 3 common here, so it is 3 into 3q square. Now we can let 3q as m. Whatever is extra, we will let it as m. So in first case, here a square is 3m, where m is equal to 3q square. Case number 2. Case number 2, what is this? Case number 2 is 3q plus 1. When squaring both sides, a square is equal to 3q plus 1 whole square. So it will be a square plus b square plus 2ab. So 3 is coming common in first 2. So 3q square plus 2q plus 1. So extra thing we will let as m. So it will be 3m plus 1. I told you so many times that we always have to keep that point in mind, that what we have to prove. So this whatever is extra, that we have to assume as m. That's why we are letting it as m. Now case number 3 is a is equal to 3q plus 2, squaring both sides. So 9q square plus 12q plus 3 plus 1, 4 we can write 3 plus 1. So in first 3 is coming common, 3q square plus 4q plus 1 plus 1. So this is extra, so we will letting it as m. So it will be 3m plus 1. So the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. We have find 3 cases. One is 3m and 2 are 3m plus 1. So we can clearly say that, hence it is proved. So use Euclid division lemma to show that the cube of any positive integer is either of the form 9q plus 1, 9q plus 8. So let a be any positive integer. We apply division lemma. A and b is equal to 3. So it will be, because it is square, so we can say that it is divided by 3. So 3 is dividing a. So m is coming. Remainder will be 0, 1, 2, 3. So number will be a is equal to 3m, or a is equal to 3m plus 1, or a is equal to 3m plus 2, because remainder is 0, 1, 2. Case 1, a is equal to 3m we have, so we can cube. So a cube is equal to 27, m cube, 9 is coming common, 3m is cube. So we can write 3m cube as cube. So it is coming, a cube is equal to 9q is coming. Case number 2, a is equal to 3m plus 1 we have. So we are cubing both sides. A cube is equal to 3m plus 1 whole cube. So what will come after cubing? 27 m cube plus 1 plus 9m, 3m plus 1 will come. On solving this, 27 m cube plus 27 m square plus 9m plus 1 is coming. In first 3, 9 is coming common, so 3m cube plus 3m square plus m plus 1 is remaining. So we can write extra thing as q. So it is 3q plus 1, where q is equal to 3m. Now what is the case number 3? A is equal to 3m plus 2. So when cubing both sides, what is coming? 27m cube plus 54m square plus 36m plus 8. In first 3, 9 is coming common, so it will be 3m cube plus 6m square plus 4m plus 8. So 9 cube plus 8 is coming. So we clearly observe that cube of any positive integer is of the form 9 cube plus 1 or 9 cube plus 8. We have completed today exercise 1.1. Thank you very much.